In this video, we're going to look at something called the stopping potential and apply it to Einstein's photoelectric equation. Now, the photoelectric effect outlines how photons of light shining on a surface will emit electrons. If those electrons are part of a circuit, then what the photoelectric effect will produce is an electric current. You can see this illustrated here. The light shines on the surface, the electrons are released, and then that forms a current, which is read here on the ammeter. Now, the advantage of using a current is that we can start taking some measurements that will tell us something about the properties of these electrons that are moving in the wire. The current, if you remember, is the number of charges per second. So you can work out the number of coulombs per second, the number of electrons given off by this surface per second by looking at the current. Now, this kind of thing happens in a photocell. And this is an illustration, a very simple photocell, where you have a surface and an anode which receives the electrons. We can see that on this following picture. Here you have your emitter, the light hits the emitter, and the electrons are received by the collector, which will be positive and attracting the electrons. This is then connected up to a circuit, a battery, and an ammeter, and that will give you a current. Now, what we're looking at today, though, is not that. We're looking at something called the stopping potential. Stopping potential enables us to find out the energy, or calculate the energy of the fastest electrons flowing. So that's what the stopping potential is going to do. It's going to help us to work out the kinetic energy of the fastest electrons that are emitted by this photocell. And the way that we do this is by reversing this battery. If we flip it and make it go the other way, then what you'll be doing is slowing down those electrons that are emitted until they stop. When you slow down the electrons until they've stopped, the energy that you've put in here with this battery supply will match the energy that was emitted by the electrons in the first place, or the photocell in the first place. If my explanation is not enough, you can use this explanation to help you. But anyway, this is the circuit diagram that we use to look at this idea of stopping potential. So what you've got here is a photocell. The electrons move across, but we put a variable reverse PD in here, going the opposite way, and we adjust it, right? So we adjust it so that it is flowing. It's making the current flow in the opposite direction. When this ammeter registers 0, then the voltmeter here will give you the voltage at which the ammeter is 0. And that voltage is called the stopping potential. The stopping potential is the voltage supplied by the photocell. It's equal. And if you know the voltage supplied by this photocell, you can work out the energy and even the velocity of the fastest electrons. Remember that voltage is energy per unit charge. There are two ways to look at this repelling voltage. The first one is a graph of current against voltage. Now here we have the representation of voltage going in the right direction and then voltage going in the opposite direction. So this is what don't worry about this too much, but we're worried about this side. What happens when we reverse the voltage? Let's start at the beginning. The PD is 0. When the PD is 0, our voltage is at this level. We have some current flowing, okay? What do we mean by PD 0? That means this isn't switched on, which is fine. It just means that the photoelectric effect is happening normally. The light is shining on here and the electrons are flowing around. Okay, so we haven't started doing this bit yet. But now we start using our potential, our variable supply in the opposite direction. And what you can see is the current starts to go down. And when we hit this magic voltage, where the current goes down to 0, that point there, we found our stopping potential. The energy we're putting in matches the energy of the electrons that are emitted. Okay, so this is a very important graph. And what we're going to do is look at what happens now to this graph if we increase the frequency of the photons and we increase the intensity of the photons. Now, if you remember, increasing the photons, the intensity of the light increases the number of photons, right? So the first thing we're going to look at is what happens if we increase the intensity of the light shining on the photocell. If we increase that intensity, what we're doing is we're keeping the photons exactly the same, but we are increasing the number of photons. And then the second thing we're going to look at is what happens if we increase the frequency. That means we go from ultraviolet to something bigger than that, say X-ray. That increases the size of the photon. So the photon is much, much bigger. So let's have a think. What happens to this graph if I increase the intensity of the light? If I increase the intensity of the light, then the number of photons increases. And each photon will release an electron. So that will increase the number of electrons flowing. If the number of electrons flowing increases, then the current increases. Because remember, current is number of electrons per second. So this graph will look like this. Without the applied voltage, the photoelectric effect will have a higher current. Why? Because there's more electrons per second. The stopping potential will be exactly the same because the photons are the same, and so therefore the energy that the electrons have will be the same. This we can figure out from Einstein's equation. The energy that we have, the energy of our electrons, equals the energy of the photon minus the work function. By increasing the intensity, we have not changed the work function. It's the same. So therefore, our energy max is the same and our stopping potential is the same. So our graph will look like this. Okay? So this is a graph showing what happens as we increase the intensity. Our current is bigger, but our stopping potential is the same. Now, what would happen to our graph if we increase the size of the photon? Now, if we increase the size of the photon, then in this equation, this section is greater, HF. Our frequency is bigger, so therefore our Emax will be larger, right? And if our Emax is larger, then our stopping potential is larger. Not only that, if these electrons that are arriving at the collector are moving at much higher speed, if they're going faster, then what you're getting are more electrons per second. The rate of flow of electrons is increased. So therefore we are going to get a higher current as well. So two things are affected. And so this time, in our graph of current against voltage, our stopping potential is now bigger. But also our current is bigger because the number of electrons traveling per second increases. So this is how both frequency and amplitude affect the photoelectric current and the stopping potential of a photocell. Now the last thing you need to know is, how does this all affect our frequency against energy graph? The one where we can find Planck's constant, the work function, and threshold frequency. Well, the amount of kinetic energy, which is normally on the y-axis, can be represented by E, the electronic charge constant, times Vs. And Vs is our stopping potential. To find this experimentally, you would try to find the stopping potential for a whole range of frequencies, right? A whole range of frequencies. And from here, for each different type of frequency, you would find a different stopping potential. Okay, so your graph would still be a straight line, but you would find the stopping potential for each specific frequency on the y-axis. Okay, and once again, you would find Planck's constant from the gradient, and you would find the work function from the intercept on the y-axis and the threshold frequency from the x-axis. It's also important to note this constant has to be used when we're drawing a graph. If we don't use it, then our calculations for the work function and Planck's constant need to then take into consideration the E value. And that's it for stopping potential.